Welcome to the Performance Tuning Architectures with the Intel FPGA Deep Learning Acceleration Suite online training. My name is Carl. In this training, we will cover how to use the Intel FPGA Deep Learning Acceleration Suite to customize architecture or bit streams to achieve maximum performance for deep learning inference tasks. Before we begin, you should already be familiar with the basics of the Intel FPGA Deep Learning Acceleration Suite. If not, please view the short Programmer's Introduction to the Deep Learning Acceleration Suite online training. This is the agenda for this presentation. We will first briefly review what the Intel FPGA Deep Learning Acceleration Suite is and how it can be used with the Intel distribution of OpenVINOToolkit, as well as discuss architecture customization basics. Next, we'll move on to cover the various DLA architecture parameters that can be customized. We'll cover the architecture generator, which will automatically produce a set of architecture parameters for a given neural network. And finally, we'll discuss the compilation process to produce a custom architecture FPGA bitstream. The idea of DLA architecture customization is simply to create a custom FPGA bitstream that maximizes inference performance of your custom neural network on a given FPGA board when performing inference tasks with the Intel distribution of OpenVINOToolkit. Although by using the Intel FPGA DLA suite, generating a custom architecture does not require RTL coding, this process still requires a lengthy FPGA hardware compilation. So as a result, it's important to note that customization is not always required and certainly not always necessary. When you download the Intel distribution of OpenVINOToolkit or the Intel FPGA DLA suite, both software packages already include a set of standard bit streams that can be used and works very well with standard topologies. Here's a review of the features of the Intel FPGA Deep Learning Acceleration or DLA suite, which is meant to accelerate inference of ConvNets. The Intel FPGA DLA suite allows users to take advantage of FPGA without going through the lengthy traditional FPGA development process. The DLA suite consists of various implementations of the deep learning primitives organized in architectures of FPGA images that are tailored for different types of deep learning topologies, allowing users to implement various networks from AlexNet to GoogleNet and a variety of other topologies without recompiling the FPGA. The DLA architectures implement optimized common deep learning primitives such as convolutions, fully connected layers, rectified linear units or ReLU, local response normalization, max and average pooling, concatenation, and many others. We're constantly adding primitives to DLA as well. When executing the DLA library architectures, the data between layers stay on the FPGA, and for very deep topologies, data just keep looping through using or bypassing the primitives that are needed for each layer. The diagram shows architecture implementation of the CNN primitives on the FPGA in a sequence of convolution or fully connected ReLU LRM pooling. In the architecture, the networks are split into subgraphs, which are mapped iteratively to the sequence in the FPGA for execution. Some primitives in that sequence are bypassable to support different combinations of subgraphs for the networks. Networks that use primitives beyond those implemented on the FPGA can be computed with a hybrid CPU-GPU FPGA solution. The various pre-built images can support many different types of network, including those listed here, but if you need to, you can also customize. You can customize the architecture through the use of architecture parameters, which is the focus of this presentation, but you can also add custom primitives to the DLA crossbar by implementing custom kernels using OpenCL. The Intel FPGA Deep Learning Acceleration Suite is part of the Open Visual Inference and Neural Network Optimization, or OpenVINOToolkit, which is a comprehensive toolkit used for developing and deploying computer vision solutions on various Intel platforms. The OpenVINOToolkit provides a seamless way of accelerating inference tasks on various Intel architectures, including CPUs, GPUs, VPUs, and FPGAs. It's expected that DLA architectures, including those custom generated, are exercised through the Deep Learning Deployment Toolkit part of OpenVINO. The OpenVINOToolkit also contains support for OpenCV and OpenVX, but those are outside the scope of this training. With the Deep Learning Deployment Toolkit part of OpenVINOToolkit, trained deep learning networks are deployed through high-level C++ function calls. There are two components to the Deep Learning Deployment Toolkit: the Model Optimizer, which converts and optimizes trained models on various deep learning frameworks and converts them to an intermediate representation, and the inference engine, which is the second part of DLDT. That's an execution engine that deploys the network by consuming the IR files through optimized C++ API. Deep Learning Deployment Toolkit can be targeted for many different Intel hardwares, including FPGAs. When executing on the FPGAs, the software part of the DLA suite is invoked, which programs the FPGA with bit streams and is built on top of the FPGA OpenCL platform. As we said earlier, DLA and OpenVINO software packages include precompiled and optimized architectures sorted by various different boards. On the right, you see the standard included bit streams for the Intel Vision Accelerator design with ARIA 10 FPGA board. There are bit streams optimized for LXNet, GoogleNet, MobileNet, SSD, TinyYOLO, SqueezeNet, etc. for both 11-bit floating point and 16-bit floating point formats. These bit streams are optimized for performance for the stated standard topologies and data types. However, better performance may be achieved with custom architectures for custom deep learning networks. This is because custom deep learning networks may have different size requirements at different layers of the network. This means the on-chip RAM requirements may be different. Custom deep learning networks may also have primitive requirements that are different from standard networks. In those scenarios, you can use the customization feature of the Deep Learning Acceleration Suite to tailor your network topology needs and create the maximum compute units on the FPGA to accelerate the inference of your network. Before we start, here are the software requirements to generate a custom DLA FPGA bitstream. First, you'll need the developer version of the Intel FPGA Deep Learning Acceleration Suite. This contains source code, Quartus hardware projects, scripts, and other tools needed in the compilation process. You'll need the Intel FPGA SDK for OpenCL Pro Edition, since the DLA FPGA project is built on top of the FPGA OpenCL infrastructure. In association with the OpenCL SDK, you'll need an OpenCL board support package for your target board. If you're using the Vision Acceleration Design or Programmable Acceleration card, then just download the appropriate board support package. If you have a custom board, you'll need to create the custom board OpenCL board support package. You also need the Quartus Prime Pro Edition software. This software is used to compile and generate the FPGA bitstream. The exact version depends on the OpenCL board support package requirements. Check the DLA Compile and Customization Guide referenced at the end of this presentation for details. Lastly, some other support software needed are Python version 2.7.1 or later and Protocol Buffer version 2.5.0. There are many ways to customize your DLA bitstream through the use of many different parameters. Now we'll discuss these architecture parameters in detail. There are many aspects of a DLA architecture that can be customized. For example, you can decide on the number and vectorization of the convolution processing element array, which dictates parallelization. You can control the data type, you can select the primitive connected to the DLA crossbar, you can dictate the on-chip cache size for both filter and feature data, and many other ways to customize. You use architecture parameters to customize these properties, meaning all you have to do is change the properties in a protobuf file and run the build script. No need to make any RTL hardware coding. The actual RTL changes are handled automatically for you. Here are some architecture parameter examples. CVector, KVector, PVector, and QVector describes the properties of the convolution processing element. Activation KVector, pool KVector, norm KVector, and output writer KVector dictates the parallelization of those particular auxiliary kernels. The filter cache depth and stream buffer depth dictate how much on-chip RAM is used for each of those purposes. There are parameters to enable various primitives, parameters to enable different data precision, and many others. We will talk about the most important parameters in this section. For a complete list of customizable parameters, see the DLA Compilation and Customization Guide. The bulk of the compute on the FPGA is located in the convolution processing element array. This is an array of convolution processing engines, each performing parallel operations. The C vector, or channel vector, is the parallelization of each of these PE arrays in the depth-wise dimension, so the operations from multiple channels in the same layer can be processed together. This parameter increases the number of FPGA multiplier instantiated for each processing element, so there is a large impact on resource consumption, but also a large impact on performance. there's an almost linear relationship to the number of multipliers used and performance of the DLA convolution engine. The default value for C vector, if not specified, is 8. The second way to parallelize the convolution process element is through the K vector or kernel vector, or sometimes referred to as output channel vector. Each convolution processing element stores one set of filter weights and can calculate results for one output channel at a time. Having a K vector greater than 1 instantiates multiple processing elements. Each of the elements can process one output layer with its associated weights, so multiple output layers can be calculated in parallel. Just like C vector, K vector linearly impacts the number of multipliers instantiated, but also increases the RAM resource usage for the filter cache. And because of this, just like C vector, K vector has a large impact on performance and resource consumption. The default value here is 24. In addition to C vector and K vector, there's also P vector, which is the degree of compute vectorization for each processing element in the height dimension, the Q vector, which is a degree of compute vectorization in the width dimension. These are used together with the Winograd transformation to increase the number of operations performed. Again, both of these parameters have a large impact on performance and resource consumption. With custom FPGA architecture compilation, you also have control over the data precision of the calculations done on the FPGA. By specifying the data precision, you control the amount of compute and storage that's needed on the FPGA, as lesser precisions will allow far more operations to be done in parallel on the FPGA, as well as increase the amount of data that can be stored on the FPGA. The DLA allows 3 precision parameters: 11-bit floating point, half precision 16-bit floating point, and standard single precision floating point. You will be able to instantiate roughly twice as many multipliers in FP11 as in FP16, and 4 times as many in FP11 as compared to FP32. As a note, only one of these data precision parameters can be enabled for a single compile. Depending on your neural network needs, you may want to enable or disable specific primitives. Primitives such as norm and pool are optional in the DLA architecture. If they're enabled, they are connected to the DLA crossbar. If your neural network uses these primitives, then it's a good idea to enable these on the FPGA for maximum performance. On the other hand, if your neural network does not use a particular primitive, it's wise to disable it so you can save resources that can be used for parallelization of convolutions. Use enable norm to enable local response normalization support. Use enable pool to add max or average pool. There are also several different ReLU options. You can use the standard ReLU as activation, but you can also enable parametric ReLU or leaky ReLU if those types of activations are used. You're allowed to only enable one of the ReLU activations. If you choose to enable the norm and pool, you'll also need to modify the architecture file to enable specific connections to the crossbar. We'll talk about that a little bit later. The parameters here enable parallelization for various enable primitives and output writer kernels. The activation K vector affects the parallelization of the enabled ReLU activation operation. Pool K vector affects the pooling primitive. The norm K vector affects the norm primitive. Lastly, the output writer K vector supports parallelization for writing of the output of each layer to DDR. The default value for activation K vector is 2, while the default for others is the activation K value. On the FPGA, there's limited on-chip RAM resource available to be used as feature map or filter cache. It's important, if you can, to keep feature data between neural network layers on chip as much as possible to avoid costly operations to the external DDR memory to increase performance. If your on-chip stream buffer used for feature data is not big enough, then between each neural network layer, the DLA engine will be required to make DDR reads and writes for the sliced feature map, which hinders performance. The stream buffer depth parameter allows you to specify the size of the feature cache, sometimes also called a stream buffer. For filter cache, use the filter cache depth to specify the desired filter cache depth. A bigger filter cache depth allows for more look-ahead filtering prefetching. The filter cache depth also limits the maximum filter size that the architecture supports. Both of these parameters significantly impacts the FPGA M20K block usage. These are the parameters that control how FPGA DSP block resources are used. The PE array DSP limit is used to specify the maximum number of DSPs that can be used by the processing element array. Increasing this value increases DSP utilization and saves adaptive logic module or ALM utilization. The ALM mult percentage parameter controls the percentage of ALM-based multipliers instantiated in the PE array. Essentially, this controls the ALM versus DSP block implementation balance. There are many other parameters available to be tweaked. Parameters for topology-specific filters and stream buffer sizes, parameters for filter size limits, interleaving support, slicing support, output image size limits, so on and so forth. Again, see the compile and customization guide for more details. Now that we understand some of the architecture parameters available, let's see how we can use the architecture generator to automatically produce an optimal set of parameters. As we've seen, there are many parameters that can be tuned in a custom architecture. It's sometimes time-consuming, error-prone, and extremely difficult to find the optimal combination of parameters for your custom neural network. The architecture generator is a tool you can run to automatically find the optimal architecture parameters for your specific neural network. The architecture generator takes 4 inputs. The first is the prototxt file. This is the initial set of architecture parameters you provide. This also provides the values for the parameters not affected by the architecture generator. The second is the XML network topology file. This is the output of the OpenVINO model optimizer, and this file provides information about your neural network to the architecture generator. The third file, the board model, tells the architecture generator the amount of FPGA resources available for that specific FPGA board. And lastly, the area model includes information on the resources consumption of your OpenCL board support package. With these 4 pieces of information, the architecture generator can then generate a prototxt file that contains a set of optimized parameters for performance. The architecture generator only considers certain parameters. All other parameters are not considered by the architecture generator, so the outputs of the parameters would just equal the value provided in the initial prototxt. This is a complete list of all parameters that are considered by the architecture generator. This includes the C, K, Q, and P vectors for the convolution processing element array, pool K vector, norm K vector, output activation K vector, and output writer K vector for auxiliary kernels, the filter cache depth and stream buffer depth for on-chip memory usage, and the PE array DSP limit to control DSP utilization. To provide information about your network model to the architecture generator, an intermediate representation or IR.xml file is needed. This file is generated by the model optimizer that is part of the OpenVINOToolkit. The model optimizer takes a trained model described in the supported format, for example TensorFlow, Caffe, MXNet, or Onyx, and then converts the network and optimizes it for inference purposes and then generates the intermediate representation. The IR actually consists of a .xml that describes the network topology as well as a .bin file including the weights. But the architecture generator only needs the .xml file and not the weights. For information on how to generate an IR from various deep learning frameworks, see the OpenVINO Model Optimizer Developer Guide. The board model and area model files describe information about your FPGA and board to the architecture generator. The board model.csv file is included with the architecture generator in the DLA download. In the CSV file, just list the appropriate board and the associated FPGA resources available. A10 is for Intel Aria 10GX FPGA development kit, and DCP represents the Intel Programmable Acceleration Card with Aria 10GX FPGA. If you're using one of these boards, then no other entries are necessary. If you're using a custom board, you'll need to enter your values in a new line. For the area model, which is also included with DLA and the architecture generator, there's information about the OpenCL board support package resource consumption. Again, in the screen capture, you see the values provided for the Aria 10GX development kit and the programmable acceleration card. The area model also contains many other information. You don't need to and shouldn't modify any information that does not pertain to the board support package. Once the inputs are prepared, you can run the architecture generator DLAC executable. When you run DLAC, set genarch to true and then provide the XML IR file. The initial architecture prototxt, the area model, and the board model file names, as well as the board name and the area model BSP name, which was used in the corresponding CSV files. There are other options available as well. check the Architecture Generator guide for complete list of options. When you execute the Architecture Generator, you should expect a runtime between 15 minutes to 3 hours, depending on various different factors. Once finished, you'll see an output prototxt file with the optimal architecture parameter values. This file is named after the graph and the board name you provide. When you run the Architecture Generator, you have the option to indicate how aggressive the FPGA resource usage should be. A larger value will result in a more aggressive value that will likely lead to higher performance. However, it also may increase the architecture compilation time as well as the likelihood of a no-fit on the FPGA. Use the --gen aggressiveness option when running the Architecture Generator to specify an overall aggressiveness from 1 to 5. The default value is 2. There are also individual aggressiveness options for advanced users. These are available to override the overall aggressiveness specifically for ALMs, DSPs, or M20Ks. For these individual settings, specify the target utilization of a specific resource. Now that we understand the architecture parameters as well as how to generate the optimal set of values, let's take a look at how to perform a custom architecture compilation to generate the FPGA bitstream. To generate the FPGA bitstream, follow the steps here. First, choose the target architecture by setting the desired parameters. Then identify the target board and verify you have the correct Quartus version or versions. Lastly, run the build script to compile your architecture. The chosen target architecture is specified in the prototxt architecture description file. This can possibly be the output architecture from the Architecture Generator, or it could be modified from one of the tested architectures shipped with Intel FPGA DLA suite. See the DLA Arch description directory for a list of architecture examples, as well as see the architecture list spreadsheet included with the DLA for a spreadsheet of tested architectures, as well as its parameter values. Before compilation, place the chosen architecture in the Arch description directory, or set the Arch root dir environment to the location of your architecture prior to executing the build script. In the architecture, you have the option to enable auxiliary kernels. Auxiliary kernels are primitives that are connected to the crossbar, for example, norm, pool, element-wise operations, or even custom primitives. If you choose to enable these auxiliary kernels, you'll need to add additional information in the architecture description prototxt to specify the crossbar connectivity as well as the configuration chain. The crossbar is where all the auxiliary kernels are connected to each other, as well as to the input from the activation, as well as the output to the stream buffer through the input mux or the output writer to DDR. The crossbar is usually not a fully populated crossbar, so you should only make connections where needed to save FPGA resource. Each auxiliary kernel has the option of connecting to the activation kernel through the crossbar, import, or any other auxiliary kernel. Each auxiliary kernel can also have outgoing connection to the crossbar output port, which goes to the input mux and output writer, as well as to other auxiliary kernels. It's important to understand the graph you're executing before specifying these connections. Here's an example of a typical DLA crossbar connection. It's important to understand that if you have two different primitives with different k-vector parameters, then width adaptation module is needed to be exerted to bridge the difference. In this diagram, since pool can follow activation or norm, we set the pool primitive to receive from crossbar import as well as norm and allow it to write to the crossbar out port. The norm primitive can receive data from activation through crossbar import or pool and can also write to the crossbar out. This example is actually a fully populated crossbar, so norm and pool can appear in any order in the executed graph. This slide shows the same connections but expressed in the architecture prototxt file. In the prototxt file for XBAR out port, we see the input from pool and norm are made. For the crossbar aux port for norm, we see that pool and crossbar in can feed into norm. And for XBAR aux port of pool, we enable the connection from XBAR import as well as norm. This makes this a fully connected crossbar, which isn't always necessary. After you've made the connections to the crossbar, you also need to modify the config chain. Every kernel must read configuration data. This includes global configurations such as size and tile size, as well as custom configuration for each primitive. The config chain is how these parameters are sent to each kernel, including those connected to the crossbar. In the architecture prototxt file, add the enabled auxiliary kernel to the config chain. The exact order does not matter, but it should be near the crossbar for best hardware compilation results. In the screen capture, we added the norm and pool to the config chain. This slide shows the complete architecture file modification necessary if you choose to enable pool and norm to the crossbar. At the bottom, we see that the enable norm and enable pool architecture parameters are set to true. At the top, we see the norm and pool are included as part of the config chain. Then for the crossbar, we add the connections as necessary according to our neural network graph. Again, this example is a fully connected crossbar. In addition to enabling supported auxiliary kernels such as pool and norm, you also have the option of creating custom primitives and adding them to the DLA. The Intel FPGA DLA suite provides support to add unary operations such as various activation primitives, 10H, ABS, power, etc., as well as binary operations such as element-wise add or molt. If you would like to add custom functionality to the DLA architecture, you'll need to write the custom primitive functionality in OpenCL and modify the architecture file to specify the properties and connections of that custom auxiliary kernel. For more information on how to do this, please see the Compilation and Customization Guide or view the follow-on Creating Custom Primitives for the Intel Deep Learning Acceleration Suite online training. Once your target architecture has been decided and created or generated, the second step is to identify a target board. This is essentially the OpenCL board support package for your hardware. You first need to ensure that Intel FPGA OCL SDK root environment is set to the location of your target board support package. Then run aoc-list boards to see a list of valid boards within the set board support package. Once you figure out the board support package, ensure the appropriate version of the Intel Quartus software is available. Make sure the Quartus router or Quartus router override environment is also set. See the Compilation and Customization Guide for more details about that. Once the custom architecture prototxt file and the target board has been determined, you can now build or rebuild a DLA FPGA image. Anytime the prototxt architecture file changes, you'll need to rebuild. Be aware the rebuilding process is lengthy because it invokes the Intel FPGA offline OpenCL kernel compiler, which in turn invokes Intel Quartus Prime software. To run the build process, just call the build.sh script along with the path to the architecture description prototxt file, as well as the target board and optionally the output directory. In my example, I'm creating a new architecture based on my custom.prototxt for the ARIA10 programmable acceleration card. Once completed, you should see the new aocx file in the build directory. To integrate the newly created aocx FPGA bitstream with the OpenVINOToolkit usage, you'll need to program the FPGA board with the aocx first. To do this, make sure the OpenCL environment script is run, and then program the bitstream using the aocl program command. Once the new bitstream is loaded, you'll be able to accelerate inference workloads through any application built with the OpenVINOToolkit Inference Engine API. This concludes the training. To summarize, we've discussed what's required to build a custom OpenVINO compatible FPGA bitstream. We discussed the various DLA architecture parameters and how the value changes can affect the performance and resource consumption. We went through the architecture generator tool, which can generate an optimal set of parameter values for your neural network graph. And lastly, we talked about custom architecture compilation. For more information, here are some additional references that can be helpful. The information in this presentation are also located in the Intel FPGA Deep Learning Acceleration Suite Compilation and Customization Guide and the Architecture Generator Guide. If you haven't already done so, view the 4 short additional online trainings listed here, which will explain the basics of how the Intel FPGA Deep Learning Acceleration Suite accelerates inference tasks, how to get started using FPGAs with OpenVINO, and how to deploy deep learning inference acceleration on the FPGA using OpenVINOToolkit. I've also provided links for follow-on creating custom primitives for the DLA training, which will show you how to use OpenCL to create custom primitives. Finally, for everything else OpenVINO related, visit the OpenVINOToolkit homepage. One last thing, when you register for this training, a link was sent to you in your confirmation email that links to a short online survey. Please complete the survey to let us know what you think of this training and how it might be improved. Thank you very much for attending the Performance Tuning DLA Architecture. Best of luck with all of your designs.